yesterday, or not yesterday, but the previous discussion we had dealt with dissolving ionic compounds and how they can break apart into smaller particles called ions, and they become aqueous because they attach themselves to water. But they don't change the basic concept as to what they are, which is why when you taste a solution with a salt in it, you know the salt is there. You know it breaks apart. It's still, by definition, sodium chloride. It's just in a different form, and that it's attached itself to water on different ends of the spectrum. The second type deals with covalent compounds. Now, technically, the dissolving reactions for these are a lot easier, but it's the understanding part that is not as easy as the ionic compounds. And I say the ionic compounds are pretty easy to figure out because all you have to do is look at the periodic chart in order to understand how they bond to each other. And it's just looking at the formula you can tell what you're going to get as a product if you are comfortable with the polyatomic ion chart. This, like I said, is an easier way of showing the dissolving of it, but we need to understand why they dissolve the way they dissolve. You are now reaching a level in your academic careers where understanding concepts is not a matter of memorization, it's a matter of deep understanding. If you really focus on why things work the way they will, then the learning becomes a lot easier. If you're trying to memorize anything, when does this happen? Well, I try to remember a process to make me remember this, like a pneumatic process. It's not going to work. You have to deep down understand. So that's my job, is to present this to you in a way that'll help you get to that point. Okay? Now, the second type of intramolecular bonds, and that means bonding with the molecule, is the covalent bond. That's the sharing of electrons between atoms, creating an inability to break apart like the ionic compounds. That bond is extremely strong. I mean, the ionic compounds are pretty strong because some of them you have to, like sodium chloride. If you throw sodium chloride on a frying pan that is as hot as can possibly be, it's just going to sit there and look at you because the bonds are so strong. But when you throw it in water, the collision of the water makes it fall apart. It's kind of hard to comprehend that sometimes, but it's strong and yet weak. Kind of like a lot of people I know. Anyway, you can identify a covalent compound, also known as a molecule. When we say molecule, we actually mean covalent compounds, by the fact that no metals or alloys are found in the compound. So all the ones we dealt with yesterday had metals in them. These will not. This is also the first time we'll be dealing with solvents other than water, although we will still deal with water in many instances. So we're far from being done with water. Water is the most common substance on the face of the earth. We will be dealing with it quite a bit. The concept of intermolecular bonds, and inter means molecules bonding with other molecules, becomes very important. There are three types that you need to be familiar with. Hydrogen bonds, which we talked about yesterday, between the water bonding to other waters, and we'll get into that again. Dipole-dipole bonds and van der Waals forces, also known as London dispersion forces. These are reliant upon the polarity of a molecule in relation to another molecule. So the concept of polarity becomes really big in this section. So let's talk about that. Here's the boring definition of polarity, and I'll expand upon it. Polarity is the inequitable, unequal dispersion of charges around a molecule. Most molecules are polar. Water is polar because of the electronegativity of oxygen when compared to hydrogen. Now, what is electronegativity? It's a new term being thrown at you. Electronegativity is the greed of an atom to pull an electron toward it when electrons are being shared. In other words, when you have a single bond, it's the sharing of two electrons. Kind of a California thing we've got going on there. So the problem is, some of them don't really want to share. They say they want to share. They want to create a stable relationship. in forming a bond with you and say, you can have this, and I'll take this, and we'll live in harmony. Doesn't work that way. Even in, subhuman situations that deal with atoms and electrons and stuff. No, it turns out that some of those things are much more greedy of electrons than others. When they are close together in what we call electronegativity numbers, then that is a pretty strong sharing between the two. If they're far apart, then that is when you've got really strong issues, and they are very easily pulled apart because one is way more greedy than the other. Now, if you look at the periodic chart, let's do that. Let's take a look at the periodic chart. There's a trend here that you need to look at. This is my favorite periodic chart on the internet because it only has the two numbers that we're going to need for this. We're trying to avoid the 3-number one because there's one group of numbers that Europeans use and it makes no sense at all. Anyway, so it turns out that the most electronegative elements are right up here. Now, the noble gases don't react. By definition, noble gases will not react because, as you probably remember, how many electrons do they have at the outermost level? Excellent, 8. Well done, you. But right here, the oxygen, fluorine, chlorine. Fluorine is the worst. Fluorine is psychotic. It will react to anything. I saw an episode of ER, which was a great TV show. Ask your parents about it. They probably watched it. In which a guy accidentally consumed some hydrofluoric acid. Hydrofluoric acid is half fluorine and half hydrogen. He died in 2 hours because the fluorine went around his entire body and attacked the tissues and shut them down. The least is francium on the lower right-hand side. Cesium, barium, radium, these are all low electronegativity. High electronegativity, low electronegativity. You see the trend is as you go to the left and down it decreases, or as you go to the right and up it increases. Alright? Cycles in their own way, but not the same way as that. You don't want to get francium and fluorine together. Oh man. You talk about a volatile relationship? Yikes. Vowels flying all over the place. Nasty words being shouted at each other. Oh, it's horrible. Kids are never the same again. So, now we talked about, so if you've got a bunch of like in the same general area around here that are bonded together, they're going to be really strong. Carbon creates a lot of strong compounds, particularly with hydrogen. Now, hydrogen's all the way over here, carbon's here, but it turns out their electronegativity is very similar. In fact, let's take a look at what electronegativity chart looks like. You don't have to deal with this, but I want you to know this trend right here that I just talked about. But you don't have to remember this chart right here, but here it is right here. You'll notice that, you may not be able to see real well, but the largest number here for fluorine is fluorine with 4.0. Oxygen 3.5, chlorine 3.0, nitrogen is 3.0. These are large. Over here, cesium, well, francium actually don't have electronegativity number because it's man-made, so I shouldn't have brought that up. But if you did, just keep it away from fluorine. Anyway, cesium is 0.7, rubidium is 0.8. These are really low over here. Carbon is 2.5, and hydrogen is 2.1, which means that the difference between them is 0.4. That's really, really small. The greatest difference is between francium and cesium, and that difference is 3.3. That's the largest possible value that we can get off of this relationship here, which means then that these are going to be crazy polar. Okay, well, in fact, that this is a metal makes this ionic and a totally different creature. So these are not even covalent here. Hydrogen, however, even though it's in group 1, will create a covalent compound And that relationship with carbon creates those strong bonds. But fluorine, let's say you put fluorine and hydrogen together, the difference is 1.9, and that's going to be a volatile relationship there. They're going to want to split up real easy. Okay? All right. So let's move on from here. Let's talk some more about what all this entails here. As I said here, the greater the difference of electronegativity between a pair of atoms, the greater the polarity. And I've included an address for the electronegativity chart if you want to take a look at it. There might be one in your book, I'm not sure, but it's not nearly as spectacular as that chart was. So what does this mean? Well, methane, which is CH4, is a nonpolar molecule. In fact,